Good evening. My name is Arabindo Tejishwar and I am a third year BTech student from the Department of Electronics and Communication Engineering. Today, I will be presenting my complete learning journey in embedded systems, starting from basic C programming concepts and processing all the way to the design and simulation of a microcontroller-based microcontroller controller. During this course, I learned the complete journey from basic C programming concepts to the practical implementation of an embedded system project. This presentation chronicles my learning process from fundamentals to the full system implementation. Initially, I focused on mastering C programming, which is the backbone of an embedded system. Gradually, I learned how software interacts directly with hardware using microcontrollers, GPIO pins, timers, and interrupts. All these concepts finally come together in a real-time microwave oven controller when timing accuracy, user interaction, and hardware control are critical. This journey helped me understand how embedded systems differ from normal software development and why efficient and real-time behavior are so important. My embedded system journey began with C programming fundamentals. First, I learned core syntax and data types, including variables, data modifiers like signed, unsigned, and volatile, and how memory is allocated. The volatile keyword is especially important in embedded system because it prevents the compiler from optimizing hardware-related variables incorrectly. Next, I studied operators and control flow, including arithmetic, relational, logical, and most importantly, bitwise operator. Bitwise operations are critical because hardware registers are controlled bit by bit. I also learned advanced concepts such as pointers, array, functions, recursion, storage classes like static and extend, and preprocessor directives. This concept allowed me to write modular, reusable, and efficient embedded code. Bitwise operation became extremely useful later when configuring registers and controlling hardware pins directly. Transition from C program to embedded systems. After learning C programming, I transitioned into embedded systems. Unlike general purpose computers, embedded systems are task specific and operate under real time constraints. They have limited memory and processing power but interact directly with hardware. Key features of the embedded system include real time operation, direct hardware control, limited resources, highly reliable. Understanding these differences helped me change my coding mindset from writing general software to writing hardware aware programs. Microcontroller architecture. I In this course I have studied PIC microcontroller architecture, particularly the PIC 16F877A. The CPU core executes instruction and control program flow. The memory consists of flash memory for program storage and RAM for data. GPIO ports allow the microcontroller to interface with external devices like LEDs, switches, LCDs, and fans. Timer and interrupts provide precision timing and event-driven execution. Understanding how this internal block works together was essential for designing a real, real-time and reliable embedded system. Hardware interfacing techniques. Next, I learned how to interface hardware components. LED control taught me how software instructions affect hardware behavior through GPIO pins. I learned port configuration, output control, and visual feedback. For switch input, I studied digital input reading and debouncing techniques to avoid false triggering due to mechanical noise. The Matrix Keypad was particularly important. Using a row column scanning technique, multiple keys were detected using fewer microcontroller pins. This requires scanning algorithms, key decoding logic, and efficient pin usage. These techniques form the foundation for user interaction in my project. I also learned about the two types of approaches for handling events, such as polling and interrupts. In polling, the processor continuously checks out for an event. While it is simple, it is inefficient because the CPU remains busy even when nothing happens. In contrast, interrupt driven programming allows the microcontroller to respond instantly when an event occurs. The main program runs normally until interrupted. For real time systems like microwave controllers, interrupts provide better performance, accuracy, and multitasking, which is why I use them in my project. Timer systems and LED display integration. Timers are the heart of a real time embedded system. I use timers to generate precise delays and periodic interrupts. By configuring prescaler and period registers, timer can be used for countdown timers, task scheduling, PWM generation. The LCD display provides real-time feedback to the user. I learned how to send command and data, initialize the LCD, position characters, and display dynamic values like countdown timers and system status. The LCD made the system user friendly and interactive. The key takeaways from these classes of the internship: technical mastery, gained comprehensive understanding of C programming, microcontroller architecture, peripheral interfacing, and real time system. Successfully combined hardware interfacing, interrupt driven programming, timer control, and user interaction in a completely working system. During this course, I was given with a project to implement a microwave oven controller using PIC. This project integrates all learned concepts into a functional microwave controller. User input is handled through a Matrix Keypad. The LCD display mode gives user the choice to select modes, temperature, and countdown timer showdown. Timer interrupts ensure accurate timing. LEDs and fan simulation, heating, and system operations were implemented. This project demonstrates a complete embedded system from input to output working in a real time world. Project overview and motivation. Traditional microwave controllers are complex and make us too difficult to study or modify them. The motivation behind this project was to create a simplified educational microwave controller that demonstrates real-world embedded system concepts. Using the PIC16F877A, this project provides hands-on experience in interrupt-driven programming, user interface design, real-time control systems. The project had four major objectives: multiple cooking modes such as microwave mode, grill mode, and convection mode, accurate timing control using timer to interrupts, temperature management for convention mode, user friendly interface using LCD and keypad. Each objective reflects real world application behavior. These are the project objectives which I have mentioned earlier. We In this project we have used Matrix Keypad, which is a 4x4 input interface for mode selection and parameter entry. PIC16F877A is the PIC microcontroller which is used for executing logic and managing peripherals. 16 cross 4 LCD display which gives us information about the temperature, time, etc. Timer 2 or ISR interrupt service routine for accurate timing control. Fan control is an output device simulating heat mechanism operation. Operational flow. The main hardware components: microwave mode, grill mode, convection mode. These are the modes which we'll be using in this. The project was implemented using the development tools like MPLAB X IDE for coding, MC8 compiler for generating hex file, picsim lab for simulation. Each component, the The workflow includes writing code, compiling it, and testing it in a simulation before hardware implementation. This approach reduces error, improves efficiency, etc. Hardware components. These are the hardware components which we are using and which I have mentioned it earlier. Cooking mode specification. There are three operating modes such as microwave mode, grill mode, convection mode. Microwave mode is a time-based operation. Grill mode is also a time-based operation which can be basically used for browning of food. Convection mode is a temperature-based operation with preheating features. The microwave mode operates for a range of 1 to 99 minutes. Grill mode also operates for a range of 1 to 99 minutes. And the convection mode temperature ranges from 100 degrees Celsius to 250 degrees Celsius. Timer and interrupt architecture. In this, we have used timer 2 configuration to generate 1-second interrupt. The ISR handles countdown decrement, LCD update, completion checks. Using hardware interrupts ensure accurate timing regardless of main program execution. Simulation rejects and project advantages. The picsim lab simulation successfully demonstrates accurate LCD output, reliable keypad input, and correct fan operation. Advantages include educational value, low cost design, modular architecture, reliable real-time operation, scalability for future enhancement like sensor and IoT. Now let's go to the simulation part. Before that, I will be showing my coding screen. This is the main code where I have given the conditional statement and switch cases for each mode. Microcontroller-C gives the timer countdown operation and the functionality when a particular key is pressed. Micro header file contains the definition for these modes. This is the file for timer. This is the file for ISR, timer header file. I will be building this code. The build is successful. Going to picsim lab. Loading hex file. Basically in this project we have implemented 4 modes: micro mode, grill mode, convection mode and start mode. When I press one micro mode, it will be basically displaying the power first, then it will be asking the user to enter the time. First I will enter for 5 seconds. 15, it is displaying 15 seconds. If I press hash, it will get entered. Before that I will be showing how it is cleared. I give a 75, giving clear, it's get cleared. I will now set for 5 seconds, press hash, it gets start. Pressing 5 gives pause and the time gets decremented. I will resume again. It will, after completing, it will give an end message as time up and enjoy your meal. Next I will go for grill mode. I press 2. It asks user to input the time. I will give us 10 seconds. Enter. Here the time gets decremented. If I press 5, it gets paused. If I press 4, it gets resumed. And if I press 6, it gets stopped and comes back to the main screen. The difference between micro mode and grill mode is that in micro mode, the power will be displayed, whereas in grill mode, the power won't be displayed. This is the difference between micro and grill mode. Other functionalities remain the same. When I press 3 for convection mode, it asks user to enter temperature. I will give us 125 degrees Celsius. If I give clear, it get cleared. I press enter. It gets preheated for 1 minute. Here we can see the time remaining. Here we have 45 seconds and the time gets decremented. After preheating, it asks the user to enter the time. I give us 50 seconds. Sorry, clear. Give us 5, or else I can give us 1 minute. If I press enter, the time gets decremented. If I press pause, it gets paused. Start or resume, it resumes the execution. If I press 6, it gets stop and return back to the main screen. These are the 4 types of mode which I have implemented during this internship period. I have implemented my final embedded system project, which is microcontroller-based micro controller. This project acted as a real-time application of everything I learned during this course. The microcontroller served as the brain of the system, while the keypad is used for user input such as mode selection and timing settings. The LCD provides real-time feedback by displaying the selected mode, temperature, and remaining cooking time. Timers and interrupts played a major role in this project by ensuring accurate countdown and responsive system behavior. Instead of using inefficient delays, timer interrupts are used to decrement time precisely every second. This improves accuracy and system reliability. Switches and control logic are used to start, pause, stop the operation safely. The LED and output control concepts are applied to simulate heater and fan operation by integrating hardware interfacing, timing, control, and user interface. The project demonstrates how complete embedded system is designed from scratch. Through this course and project, I gained a strong practical knowledge of embedded C program, microcontroller architecture, peripheral interfacing, and real time system design. This learning experience has built a solid foundation for me to get advanced in embedded system domain. Thank you so much for the Ematex for giving this wonderful internship opportunity for me, and thanks for considering this project. Thank you so much.